Hello everyone, today we're going to learn lesson 15.2 and that is on graphing logarithm functions. And we call that logarithm functions are inverses of exponential functions. So we're going to use the properties that we have learned in the past regarding transformation to apply that to graphing. So first, let's take a look at a list of some examples of logarithm functions. And again, because they are from exponential functions, let's match each of these with the inverse functions, which are exponential functions. And so the inverse for this first one is going to be based on the base right here is going to be 2 to the x. So that is the inverse, the exponential function that is associated with the logarithm base of 2. Likewise, the second one is going to have f of x inverse is going to be, the base is actually 10 when there's no, remember when there's no number with the base, it's actually 10. So this is going to be 10 to the x. And finally, this one over here is the logarithm. Natural log, natural log is the actual base, remember, of e. So this is actually e to the x, that is the inverse of that. So based on those, we can go ahead and identify the differences between the inverse, the log with exponential and logarithm. And take a look at the first one right here. We have the inverse is 2 to the x. And so the graph is going to look something like this. And the second one also going to be 10 to the x, is going to still look the same way. Notice that when we graph the logarithm and exponential functions on the same set of axes, it's going to look like they are inverses of each other. So, and let's take a look at the characteristics. So for the logarithm functions, the domain is going to be to the right of the graph, because notice the graph all sit to the right side of the y-axis. So x is going to be greater than 0 for the domain for all of them. And notice that the range is going to be going up and down, so it's Oreos for every single one of them. All the logarithms have a range of Oreos. And that would actually make sense. Again, remember the inverse has the opposite, which is domain Oreos, and then the range is going to be y greater than 0. So that would make sense. And behavior-wise, as you go to the right-hand side, the function approaches positive infinity on all of them. So that is that's true for all of them. And that's, as you go to the left side, you're going to the negative infinity. So it's approaching negative infinity for all three of them. And we have something called a vertical asymptote. Remember that for the inverse function and the exponential, we have a horizontal asymptote. So this one we're going to have vertical asymptote, and that is this y-axis right here that the graph will not cross. So all of them have a vertical asymptote of x equal to 0, and there are no horizontal asymptotes. The x-intercept is actually, instead of having a y-intercept like all of the exponential functions have, so you'll notice that the y-intercept is here, here, and here, but for the logarithm functions, you have something called the horizontal x-intercept instead. So here are the x-intercept, and notice that they're all at 1, 0. So those are the characteristics. And then taking a look at the y-intercept, there are none because it does not even cross the y-axis. And the function is positive from 1. So notice that there's kind of like two intervals broken down. One is at where the x-intercept is. So here's one interval, and then the other one goes from here all the way to infinity. So on all of them, the graph is positive from the number 1 and beyond. So that's positive. And the graph is below, which means negative, between 0 and 1. So that's what is true about all of these. And those are all the characteristics for a logarithm function. So they all have the same stuff in common, and that's the family of logarithm functions. And now let's take a look at the transformations that is going to help us to graph the functions. And so based on the equation, A is going to tell us whether the graph is going to have a vertical stretch or compression. And H in the middle here is going to tell us two things. One is going to be the vertical asymptote, and then also it's going to tell us the domain. So the domain, remember the graph goes to the right-hand side, so therefore it's going to be greater than H. And then you're going to have a vertical asymptote at x equals H. And so that's the vertical asymptote. And then K, the number in the back, is going to tell us whether the graph is going to go up or down. So left, right, and up, down. So that should be very familiar for us because we've been learning that all year long. And here are the reference points for the function. We have 1, 0, and then b for the base, 1. So those are the two reference points that we're going to need. So remember those 2 points. Let's take a look at the first example and how to graph logarithm function. So given this example here, the first step we're going to do is identify the transformations. So based on the transformation here, we're looking at the equation. We have a vertical stretch factor of 5. And then here we have the function is going to shift 2 units to the left. And then -1 is 1 down. So those are all the transformations that are dealing with this equation. Second one, we're going to state the vertical asymptote. And remember, it is h. So we can set x plus 2 greater than 0. And so therefore, x is going to be greater than -2. And then we actually have the line x equals -2 is going to be our vertical asymptote, which is like right there. So the first thing we're going to draw is the vertical asymptote. Next, we're going to use the reference points to help us to find the rest of the graph. So based on the equation, 2 units left, remember going to the left is subtract, so it's x minus 2. And then we have the graph of 5y minus 1 is the vertical, the y value. So 5y minus 1. And then let's bring down the 2 points for reference, 1, 0 and b1. So 1, 0, and in this case, b, the base, is actually going to be 2 right there. So it is actually 2, 1. So those are the 2 reference points. I'm going to use the transformation formulas to help us to derive the points. So that's going to be -1, 0, -1, and 4. Doing the math, those will be the 2 points, and we're going to graph them here. So -1 is right there. 0, 4 is here. So based on those 2, and we know the shape of the logarithm functions go something like this. So that would be a representation of what the logarithm function given this equation right here looks like. Last thing is state the domain and range. So as we know, the domain is going to be based on here. We actually already did it. So x is greater than -2, and the range, so this is the domain, and the range is going to be all reals for all logarithm functions. And that is the end of the problem. And we're going to try another one. So if you want to, you can go ahead and pause the video this time and give it a try before you look at the answer. And let's take a look at the transformations for here. So we have a vertical stretch factor of 3. And then we have a 4 unit to the right. And then based on that -2, we have 2 units down. So those are the transformations. And the next thing is a vertical asymptote. We have x equals x minus 4 equal to 0, and x equal to 4 is going to be our vertical asymptote. So we're going to draw the vertical asymptote just like that. And while we're here, we can actually go ahead and use the reference points next to find the equation. So 4 units to the right, that's x plus 4. Remember, going to the right is add. And then based on the equation, it's going to be 3y minus 2 for the vertical. So it's 3y minus 2. And the reference points, again, are 1, 0, and then b1. So the base here is actually 6. So 6 is the base. So it's going to be 6 1. And those are the 2 points, and we're going to do the math. So it's going to be 5, 10, -2, and 1. So the first point is 5, -2, so that would be over here. Second point is 10, 1. It's right here and here. And so we're going to draw the graph, and it looks something like this. So this is what it looks like. Finally, state the domain. The domain is going to be, notice the graph is to the right side of 4. So it's x greater than 4, and that is the domain. The range is going to be Oreos for all logarithm functions, and that is the end of the problem. And here's another try it. Again, pause the video and make sure that you have tried the problem before you look at the answer. And here is the solution. So based on the equation here, we have a vertical compression factor of 1/2, and then we're going 1 unit to the left. And going 2 units up. So those are the transformations. And the vertical asymptote is going to be x plus 1 greater than, actually we can set it equal to 0 to solve it. So x equals -1 is going to be our vertical asymptote. So here it is, the vertical asymptote. And then the reference point is going to be using the formulas again. Going 1 unit to the left is going to be x minus 1. And then from the equation, we have 1/2 y plus 2. So it's 1/2 y plus 2. And the two reference points are, again, 1, 0. And the base is actually no number there. But remember, that's a 10 right there. So it's 10, 1. And using those 2 points, we're going to obtain our points. And that's 0, 2, 9, and then 2.5. So based on that, we're going to graph 0, 2 is right there. And then 9, 2.5, which is right there. It's very flat, the graph. So it's flat, something like this. And then the domain is going to be x greater than -1 because it's going to the right side of that -1 right there. And then range, again, is Oreos. So that is the end of that problem. And hopefully you are able to graph the problems on your own now. So don't forget your assignment. You can go ahead and get started. The book set, the HRW 15.2, get started. And then copy notes for 15.2, day 2. And don't forget Alex. And have a good day.